Hello, I'm Hoang Lam. I'm going to present you my OPAMP design for the analog class. So here's the overview of the circuit. I'm trying to reconstruct LM741 with two NPN transistor and PNP transistor. They are 2N222 and 2N2907. I'm going to assume all the electrical characteristic like early voltage beta and reverse saturation current of the transistor will be similar to the actual 2N222 and 2N2907 since I'm using these two transistors to reconstruct the circuit. So here's the circuit breakdown. I'll go into the detail part later. Right now I'm going to give you an overview. First, we have a voltage current reference in the center. So you can see there's a several current mirror building around this current reference, and this current mirror is going to supply the current to different components based on this reference current in the center. On the left we have a differential amplifier input. This is the input stage, and then the supporting current mirror for this is this two. And then in bottom right here we have a class A amplifier, which is the main gain. And then on the right hand side we have output stage, class AP amplifier supported by some short circuit protection. Then let's move on. Before I go into the detail, I want to tell you the setup of the schematic. So this is the setup I'm using when I'm going to explain it in detail. So I'm going to use a 40 millivolt peak-to-peak sine wave with a 5000 Hz input, and I'm going to supply the circuit with a plus and minus 15 volts, and I'm going to use a feedback resistor 5K and 2.5K for the input resistor. So we're expecting a gain of -2 since we're feeding this to the negative terminal of the circuit. And then we're going to compare the result against the actual LM741 component from pre-spliced library. So the setup will be the same. Just the component we're using is the actual one. Here in the center we have the reference current. Center of the circuit is the reference current circuit. So this is built up with two transistors Q12 and Q11 and a resistor R5. This is going to create a reference current in the center, and then all the other stage will use this as a reference. So we are here in the input stage. This is a differential input. First we are building our current mirror from with this Q8, Q9, and Q10 and Q11. Q10 and Q11 is feeding the current to the base of Q3 and Q4, and Q8 and Q9 is feeding the current to Q1 and Q2. Q1 and Q2 is acting as an emitter follower. The purpose of having emitter follower here is we want to create a very high input resistance, and then this signal will be collected from the base of Q2 and Q1. This is the inverting terminal. This is the non-inverting terminal. The inverting is also known as minus. Non-inverting is also known as plus. And then the signal is going to feed into this differential input, differential amplifier, Q3 and Q4. And then down here we have the supporting loading setup. So Q5, Q6, and these three resistors down here is going to act as a, and also Q7 is going to act as a loading circuit for the input stage. Here this is going to provide a gain, and the output is taken at this point, the collector of Q6. We're expecting a gain around 0.6. So here we look at the input. So a 40 millivolts peak-to-peak input is going to give us around a 0.6 of gain. It's a bit noisy, so we try again with a 2 volts peak-to-peak input with a much more cleaner output from the first stage. Then let's move on to the second one. So the second stage is the main gain stage. The signal from stage 1 is sent to Q18 here. Q18 and Q7 is acting as a Darlington pair. I'll go into the detail later. Q18 is a emitter follower also. The purpose of having an emitter follower here is we want a very high input resistance. This is going to prevent the gain loss from stage 1 since because of the loading effect is going to be minimized because of the high input resistance impedance. And then Q7 is going to act like an emitter amplifier, and we're using an active low from Q12 and Q13. This current mirror is going to act as an active low. So I want to talk about a little bit more about Class A amplifier. So here we actually have a Class A amplifier configuration in the second gain stage. The Darlington pair Q18 and 17 is going to perform like a single transistor with a beta value of beta square. So the beta square is going to help us on having a very big gain. And then the loading, no loading resistor is going to performed by this current mirror here. The benefit of using using current mirror is we have a good output impedance, and also we can minimize the power disposal. So here's the equation for the output resistor of the current mirror, and then yeah, basically we're going to output this signal to the final stage. Oh, and also we have a Miller compensation. This is a 30 pico farad capacitor sitting here. It's going to provide us a very low 3 dB cutoff. Sorry, I mean for the lower side of frequency, we are going to have a better frequency response because this cap is going to create a dominant pole compensation. And then again, the output is taken on at the Q17 collector. Okay, here we are seeing a much cleaner output waveform from the second stage, the gain stage. So here's the final stage. This is the output stage. The goal of this stage is to provide a very low output impedance, but also still be able to supply a very large loading current. So here we have a Class AB configuration formed by Q14, Q20, and Q16 and R7, R8 as a biasing. And the output is taken at the center between these two resistors. Ideally, Q14 and Q20 are supposed to have a larger area because with the larger area we can supply a higher loading current without having too much trouble on the temperature effects. And then here's an example of a typical Class AP configuration. We can see a NMOS and PMOS here. So this Q14 is an NMOS, NPN. This is going to handle the positive side of the signal. When the signal is in positive, this NPN is going to be turned on and amplify the positive side of the signal. And then on the bottom, this PMOS is going to handle the negative side of the signal, amplify that one. However, this two transistor is a BJT, so they have a 0.7 volt before it turn on. So we need a biasing circuit to keep these two transistors always be on. So here we have a Q16 with two resistors to bias it, so that to make sure these two transistors are always on. And also we are getting the current bias from this Q13 current mirror, which is getting mirroring from the current reference. Okay. Also we have a short circuit protection. You can see this Q15 is limiting the current flowing into Q14. Right here I'm using the schematic from the actual datasheet. There's a small difference between the textbook and the datasheet. On the right hand side, we see the textbook, we have a Q15 protecting Q14, Q21 protecting Q20. However, on the actual LM741 schematic, they only have one, and it's also a little bit different in the biasing configuration, but they are serving the same purpose. Because we're trying to compare the characteristic against the actual one, so for this project, I'm going to use the actual schematic, not the book, one for the book. So here we want to, I want to compare the output, final output, between the actual LM741 and my reconstructed one. Here we are seeing an input waveform of 40 millivolt peak to peak with an offset of 0, inverted. We expect a gain of -2. So here we see a peak to peak 80, which is the same as the real one. So they match. Oh, I forgot to mention. Also in this stage, the second stage is not centered at the 0. Not centered. The DC bias is not. Is a little bit different from the input, and this output stage is also going to handle that bias, DC bias for the circuit. And then another example of the output is I'm feeding a 2 volt peak to peak input with a 1 volt offset, and then we are expecting a -2 gain. So here we see the output bias here is -2, -2. Originally we have a 1 volt because of the gain is -2, so now we have a -2 volt bias. And then the 2 volt peak to peak also became a 4 volt peak to peak, which is matching the actual one. Okay, so DC analysis. For the DC analysis, we open all the cap and then we short all the input signal. And then here are the DC current DC analysis values of the current. I'm not going into too detail. I have other couple slides when I'm going through the electronics characteristic. I might come back to this. And then we also have the voltage, DC bias voltage for the whole circuit. Here's the frequency response of the circuit. Since we are using bipolar like NPN and PNP instead of CMOS, so our frequency response is not as good as the actual one. So we have around 30 kHz is our cutoff. Let's see why we have this weird behaving. So we are looking at the stage 1 frequency response. So around 30, this thing go up, and then on the second stage, the green one is final output, the yellow one is the second stage to output. So we can see the frequency response on the second stage is probably okay. So I think probably the problem here is the first stage. Since we are using NPN and PNP, it's not an ideal solution, but yeah, the cause of this non-ideality is caused from stage 1. And then let's go through the voltage swing. For the voltage swing, we are having a DC input from -10 to 10. We are expecting a gain of 2. -2. So here's the setup. So we can see this is the actual LM741. We're expecting something like this. Should be around a little bit less than -15 and +15, since this is our voltage supply. And here, this is my reconstructed schematic. This is not as good as the original one, but still we have about 14 volts. The software I'm using have a time limitation of 15 minutes. I'm going to continue in the next video.